I'll let Dr. Stadler take it away.
Thanks, Mehdi. Yeah, it is too bad I can't visit you in person and see your labs, and that's my favorite part. Like the lecture when I traveled around for a year, just seeing everyone's lab is so exciting.
Hopefully, hopefully in the future.
Yeah, hopefully. You asked about the weather in Minnesota. I think we're doing better than Texas, so that's saying a lot. And I can't resist our favorite joke, which is when someone says it's freezing out, like it is today, a Minnesotan says, "Thank God it's not cold yet." Because freezing is quite warm on our scale. Anyway, right. So I actually have two parts to my group, and I just want to say that up front in case anyone's interested in optics. We also combine magnetism and optical properties to make things like diodes for light in integrated circuits, in photonic integrated circuits. So we'll have a diode that we can put in there or an isolator to prevent back reflections from hitting the laser. But that's really a whole different part of my group. And so today I want to talk about the work that my group does in bioapplications of magnetic nanowires. And I thought for this talk, I would focus on biocomposites, barcodes, and heaters, and I'll explain what those are. So I think we should start with what is a magnetic nanowire in case anyone doesn't know already. And then really the reversal mechanisms are the way you can control the magnetism at this very small scale. So I'm going to go into reversal mechanisms quite a bit. And then I'll also describe the projection method for decoding, which is something we use for a lot of the applications that you see below. And then the actual applications, I have them kind of separate. So I'm going to call out in the talk when I change from fundamentals of magnetism and nanomagnetism and start talking about the applications. I'll call out each one as I get there, just to kind of help you keep track of the talk. One thing we always joke about is it's nice to know how many slides there are when you're watching a talk. And I have, I think, 47. So as you're looking at the page number, you can sort of gauge where I'm at. And I know that can help when you're listening. So first, what is a magnetic nanowire? It's actually a very long, let me ask, can you see my arrow or should I switch to a laser pointer? It's a long...
We can see your arrow.
Oh, good. Okay. Sometimes there's a way to put a laser pointer, but this looks good. Yeah, so it's a very long magnetic material. It can be any magnetic or non-magnetic, but we mostly work with metals. So for example, here I'm showing from Mazin's paper a while back that was copper, and then we put in some cobalt copper layers, and then we had more copper to be kind of electrodes that we could contact. And we grow these in templates so they could be in arrays. One hard thing about that is, you know, it's hard. In this image, I could kind of smear out the oxide so you can see the nanowires. But when we're actually imaging them with something like scanning electron microscopy, the images can be pretty foggy like this because there's actually oxide all around the nanowires. And so what we'll do is kind of take our template and break it and look at the edge. And Joseph actually realized you could use the backscattered electron mode. And if you happen to have gold iron, which is what he was working with, and we should try it with the cobalt copper, the gold plasmonics, well, it's not really plasmonics, they're just a heavier element, so the electrons scatter off it much brighter than on the iron. So it's kind of a nice way to observe the homogeneity of the whole sample without needing to etch the oxide away. So a lot of the images I'll show you in the rest of the talk, we've actually removed the oxide from around the nanowires to be able to see them. Right, so here is how we make them. We start off with some kind of template, like this is anodic aluminum oxide. And this is an oxide that has nanopores in it that are columnar, long, circular columnar pores. And what we'll do then is coat one side of that template with something. We've experimented with a lot of different contacts, but we coat that, let's say, titanium or tungsten as an adhesion layer, and then maybe a 200 nanometer layer of copper, which is our electrode. And then we encase the entire back in a polymer so that when we put this sample now into an electrolytic bath, like I'm showing here, the sample, only the pores are open to the electrolyte. So when you apply a voltage between the counter electrode and the reference electrode, now I'm going a little crazy here, we actually will apply a voltage between the working electrode, which is our sample, and the counter electrode. But we measure to know what exactly is the voltage at the working electrode by having that reference electrode sitting there. And that's kind of important because otherwise there's things like, I mean, my mouse is going a little nuts. There could be an ohmic drop across the bath. There could even be maybe a little bit of a counter reaction at the counter electrode. So we want to make sure that we know exactly the reduction potential of the metal that we're trying to grow, and that we match that voltage with some desired over voltage, which is what drives electrochemical deposition. Now, what happens is the metal can't deposit on top of the oxide. So the only place the cations can come out of solution and turn into a metal, grab 2 electrons and reduce to a metal, is actually down inside the pores on this electrode down here. Because like I said, we encase the back, so it's not exposed to the electrolyte. And then you just build up atom by atom as you electroplate inside that pore. And so here I'm showing where we might have grown gold and then iron and then more gold. And in this case with Anirudh Sharma, that's exactly what we did. And this work was done with Alison Hubble, who's in mechanical engineering here. So that was kind of one of our first uses of nanowires in bio. That's why I thought I would start with that example. A lot of our papers kind of show you how to grow a nanowire as you're starting to read the paper, but I picked that one because it was the first time we put nanowires in a cellular sample. So what are the templates? Well, this is actually a picture of the top of aluminum oxide. We also grow nanowires in track etched polycarbonates. The oxides are kind of nice because we make them ourselves pretty readily. It's also an electrochemical technique. Anodization basically means you make aluminum foil or aluminum film on a silicon wafer. You make that the anode of your electrochemical cell, and then you apply a voltage between your anode, which is your sample, and a cathode. And as this metal, which is aluminum, as it oxidizes, because it's the anode of your electrochemical cell, there are no cations in that particular case. We're simply growing the template. So you put in your aluminum, you make it positive because it's going to attract the oxygen. It oxidizes the aluminum, and the oxide that forms has these pores in it. So it's kind of a remarkable self-assembly process that just happens naturally when you apply a voltage to aluminum to oxidize it. So we can grow these pores. This is just one example. I wanted to break it and show you the side so you can just see how very long and narrow you can make these pores. So this is unlike anything where you would try to do a top-down lithography where you have a film and you want to put down some photolithography dots and then etch a nanowire by etching away a film. You couldn't have a very high aspect ratio doing that. But here you can see we actually have a really high aspect ratio, and the nanowire starts to form down at the bottom of the pore and then just grows up the pore as long as you want to, in that case, apply you apply a negative voltage because you're drawing cations over and they're going to go inside the pore. So there's 2 separate things here. We make the template, which looks like this, and then we take it out, rinse it off, put the contacts on the back, and then we put it into another electrochemical bath where you have cations. And when you draw the cations over, they fill up the pores. And if you want, you can remove those wires from the template and use the wires as individual barcodes or nanowarmers or some of the other things we're going to talk about. So I'll assume that this audience knows enough about electrochemistry that kind of makes sense how we make the nanowires, and that we can control the material that we put in the pores, either by changing baths, so a gold electrolyte to an iron electrolyte back to a gold, or you can also have, if you have a more noble and less noble metal, you can change the voltage and you'll get the gold to deposit, then the iron, then the gold, then the iron. So we've done both, and these are examples of papers where we talk about those techniques. So I wanted to show you just some pictures. I said I would sometimes remove the oxide so you can just see the nanowires. This is a fracture surface, so you can see the wires right at the edge broke when we broke the sample to be able to look at it. But here's some copper we put in the bottom, just kind of to get the growth started. And then we grow gold. And then this is iron cobalt, which has a very high magnetic moment. And then another little bit of gold at the tip. This allows us to functionalize the tips with something like a thiol and then a peg. And it leaves the magnetic component uncoated so that it doesn't oxidize. And you can use, you can even functionalize with two different things, something like histamine that would functionalize the iron and be labeled to maybe a drug you want to deliver to a tumor. And you could functionalize the gold with something like PEG to functionalize to something else. So it's kind of nice to have many different materials so that you can functionalize with a multi-mode application if you want to. So we can make these nanowires from 10 nanometers in diameter all the way up to 200. And they can be as short as 10 nanometers if we just start to grow and then stop. But usually we make pretty long wires if we want. So for example, in cellular applications, something on a scale of microns is very readily internalized by cells, like these two images here. But we'll also make longer wires when we want for things like MRAM or barcodes. So now that we have magnetic nanowires, the question is, how can we characterize those nanowires? So I might assume that this audience is familiar with hysteresis loops, and in case you're not, what we're plotting on the bottom is an applied magnetic field. So the magnetic field is pointing to the right on the plus side of 0, and when we swing back to the negative side, the magnetic field is pointing to the left. So we just sweep the magnetic field from fully to the right, pull it back to 0, and then send it to the left. And so when we do that, you might be familiar with the idea that these nanowires might have all of their moment aligned along the field at high fields. And as you switch to negative fields, the moments would switch to apply along the negative field. And that's roughly what happens. And you're probably also aware that if you have a magnet like I'm showing you here, you'll also have dipole fields coming off of those magnets. And on the nanoscale, that can impact the way your entire device works. So what are the characteristics you look for in hysteresis loop? Well, there's MS, which just says saturation moment. All my moments are lined up along the field. So I've applied a high enough positive field or a low enough negative field that all the moments are lined up. And the value in the y-axis tells me how much moment does that sample have. So iron has more Bohr magnetrons per atom than cobalt, and nickel is the one with the lowest. So even if you have the same volume of iron to cobalt to nickel, you'll end up with ratios like this. Now, what about MR? Now I take away the field and I don't have MS. So the moment didn't stay lined up along the nanowire, but I lost some moment in the direction I'm measuring the moment. So in this case, I'm measuring the moment in the same direction I'm applying the field. And I'm guessing that what's happening here, because we're measuring an array of nanowires, is that the dipole fields are influencing other wires. So one of the wires switches because the other dipole fields are pointing down on it. So it's seeing a smaller field. At 0, it's actually seeing a negative field because of the interaction field it sees from the other wires. And then the other thing that we look at a lot is the coercive field. What is the field you need to make your moment 0? So you have as many wires pointing left as you have pointing right when you're at that coercive field. Now, unfortunately, this hysteresis loop tells you a fair amount, but if you want to combine wires, you'll find that you just get a sheared loop, and it's pretty hard to distinguish how many of one versus the other you have. So you couldn't really use just a simple hysteresis loop to determine a barcode. Now, before we talk about what you can use to distinguish barcodes, you really have to think about how does that moment reverse? We just said all the moments are pointing right and then they all flip to left, but how does that happen? If you have a very small particle, it could be that all of your moments along one nanowire just rotate to face the other direction. That's called coherent rotation. But it's a little more likely that, especially if you have a long wire, that the moment on the end will start to shift and then lay down, and then the next moment will flip. And you basically, like dominoes, flip one, then the other, then the other, then the other. And this is called the transverse wall. How many of those moments are in the process of flipping so that this is, the one side is pointing to the left, but the other side still pointing to the right. And the moments in the middle are the ones that are in the process of flipping. So there can be a thickness to that wall, they call it. Another thing that can happen when you have slightly bigger diameters is instead of all of your moments just rotating with coherent rotation, it might be that you actually form a vortice. And I'll show you that later. I actually removed the movie from right here, I think, because I didn't want to confuse the issue. But just like with the transverse wall, you could have the case that instead of the entire nanowire forming one big vortex and switching, maybe you just form a vortex right at the end of the nanowire. And then that vortex wall propagates through like dominoes, one after another moment switching as the field propagates through the wires. So that's called coherent rotation, the transverse wall, curling, and then a vortex wall. And all of those have different characteristics that we could try to trace. So one example of that is angular dependence of reversal. It turns out that if we apply the magnetic field, let's say this is theta equals 0, so the field is being applied along the nanowire axes, we might have a very square hysteresis loop like the one you see here. But if we apply the magnetic field at some angle, we'll find that the hysteresis loop changes. And the reason for that is what we're measuring is the moment that's pointing along the field direction. So let's take the case where the field is applied 90 degrees to the nanowire axes. When you reach 0, you're basically forcing all those moments to align along the field, which, look at the figure here, right? The moment wants to be aligned along the nanowire axes due to what we call magnetostatic energy. And as you apply a magnetic field perpendicular, you kind of force the moments to come perpendicular to the nanowire, which is a very high energy state. So when you take that field away, the moments go back to being along the nanowire axes. And so when you're looking at M in the same direction as the field, when you take the field away, well, all the moment has rotated 90 degrees to the measurement direction. And so you get net 0 moment at that point. So the key is to remember when M equals 0, it doesn't mean there's no more moment. It just means that it might not be pointed in the direction you're measuring, or it could be that you have equal but opposite moments at that point. Okay, so here's one example of using hysteresis loops measured at different angles. And when they're actually in an array, like you'll see here, these are 30 nanometer diameter nickel nanowires. And we have a fill factor in our array of 0.5%. So these are pretty thin nanowires, pretty far apart. And you do see behavior, something like what I was just describing, but it doesn't go all the way to 0 remnant moment at 90. And then if we make our nanowires slightly bigger, so this is 50 nanometer diameter, fill factor a little higher, we do see this is closing up a little bit. But by the time we get to a higher diameter and a larger fill factor, this is going to be pretty hard to distinguish. And what some people will do is plot the coercivity. What field is it where there's 0 moment? Plot that versus angle. So you can see, especially in this 50 nanometer case, if I were to draw a line here to 0, you would see a pretty big dip here at 20 degrees, and I think that's actually 90 degrees. And so these are what the plots look like. The behavior is somewhat different, but not so different. It would be hard for me to distinguish which nanowire do you have based on the shape of that curve. So we're kind of back to really just having what's the coercivity, because where these curves start is pretty distinct. But I've already mentioned that can be a difficult thing to really pull out when you mix nanowires together. If you give me one nanowire type and ask me to tell you which type that is, I could tell you, oh, it's got a coercivity of 90 millitesla. That means it's going to be a 30 nanometer diameter nanowire. Or it has a coercivity down at 20 millitesla. That's a 200 nanometer diameter nanowire. But if you want to mix them together and have me tell you how much is in each sample, I probably couldn't do that just using coercivity. So that's where we get to a somewhat more complicated measurement called a first order reversal curve. And this is just a beautiful technique that was developed decades ago, actually. And I should have put that reference on here as well, probably. But if you look at fork, it's been called that for a pretty long time. It was based off of a method that was called the Prasok method, and Stancu actually developed that, S-T-A-N-C-U, so Stanchu really. He developed this fork technique using what's called the Prasok model, which would say what if each nanowire is its own little hysteresis curve? So we'll call that a hysteron. And then if you have a whole lot of nanowires together and they each switch with a similar hysteresis loop, could we then back out of a measurement like this which nanowires are present in your sample? So you apply a saturating field, and we should have taken out the glass rod that's holding the sample, because that's why this goes negative here. But the sample itself stays flat. This is one of our first fork papers. So you saturate your sample, and then you come to what we call a reversal field, without measuring. You just jump from saturation field to this reversal field, but you measure your way back. Then you jump to another reversal field, and step by step by step, you work your way through these curves, measuring your way back every time. And then they plot these things called Fork histograms or heat maps, which is basically taking the double derivative of what you're measuring and plotting where that happens. So a double derivative, for example, is what's the difference in slope between successive curves. And I'll get to an example that you can see that better, but you end up plotting curves like this where coercivity can be the x-axis and interactions between the wires ends up being the y-axis. So if you look at this, these are two nickel nanowires, nanowire samples, so arrays of nanowires. The one is 3 micron long nanowires and the other is 6 micron long nanowires, as labeled up here. And so we see less interactions when the wires are shorter, but the coercivity is about 100, let's say maybe 150 Oersted. And when you come over and make the nanowires longer, there's more interaction, but when you drop down to the coercivity, you're still at about 150 Oersted. So this looked pretty promising to us because we identified a coercivity and the interactions are separated out by being plotted on the y-axis. So the idea would be if you mix samples that have different coercivities, you'd see a dot along the x-axis, whatever interaction is happening. And we had a subsequent paper that showed that works to some extent. But I should point out these curves take a long time to measure. So I want to show this, which is work that's just been accepted to Intermag 2021, because I like the way Reza has plotted the way you measure these curves. You saturate, then you come to reversal field and you come back. And you don't really know when are you going to drop down in moment because all you're doing is applying this field and then hopping and you apply fields, another field, jump to another field, right? And you just keep applying those fields and then you measure whatever you get out. So you might measure a lot of curves that actually don't have any wires reversing yet. If you start your reversal field measurements up here, then you get to the spot where something reversed and is pointing to the left now. And then when you sweep your way back, that flips to go back to the right. Then you go to another reversal curve and more of them flipped because we have less moment here. And you sweep your way back and you can see that they all switch back to being fully to the right. And you have to work your way through those measurements. It can take a pretty long time. And even generating these simulation heat maps here takes a long time because you actually have to go and apply each of those fields that you see a dot for. And what you're trying to separate out is, if this is a historon where a single nanowire is switching from fully right to fully left, just one nanowire, it really can only be left or right because it's pretty energetically unfavorable for the moment to not be fully left or fully right. I'll kind of leave it at that for magnetostatic reasons. But what happens if it's seeing this HU is it's seeing a field being applied to it by the other nanowires around it. So it has a certain coercivity, which is basically from the middle of its historon to where it switches. And it's equal then in both the coercivity I pointed to before is going to be, the delta here from mid to the side is the same either way because we're talking about being in the middle. But where that middle line shifts from 0, we are going to credit that to the fact that it has interactions from other nanowires. So here, Reza has simulated what happens if I have one coercivity and no standard deviation in coercivity between all my nanowires. But I have an interaction field of 0 and a distribution in interaction fields. So some wires aren't seeing any interaction field, but others are seeing 20 Oersted. Your fork heat map would look like a long line like we just saw for nickel that has a certain coercivity and then you see the hysteresis or you see the distribution of interaction fields on the y-axis. Same thing if he plots that actually there are no interactions, the wires are far apart from each other, they don't see dipole fields being being sent through them by the wires around them because they're so far apart. But I'm going to allow the coercivity to have a distribution. Maybe my nanowires aren't exactly the same size. Maybe there's something about the tip that makes one form a vortex wall before another. Well, the heat map and fork would look like this. As you'd expect, there's a distribution in coercivities, but there's no interactions. And then as he dials in interaction and then more interaction, you end up getting these curves that you can see here. So that can try to help explain what we actually see in experimental effects, and that's what these are. So these are nickel nanowires that are varying in diameter. These are all, I think he did 2 micron long. So even the one that is down here, these are 100 nanometer in diameter, 2 microns long. That means they have an aspect ratio of 1:20, which is pretty hard to do with lithography. So it's one of the reasons we like this growth technique. And what you see here is as the nanowires change from 30 nanometer diameter to 50 to 100, the coercivity is shifting from about 100 Oersted to about 60 Oersted to whatever this is, like 0.4, 0.3. My eyes, unfortunately, I should be having my reading glasses because I didn't get to use my big screen, or the sound system wasn't working. But you can see anyway, there is definitely a shift in coercivity as you make your nanowires larger in diameter, and that's because of the reversal mechanism. When we get to 200 nanometers, we're going to be able to have a vortex wall. These nanowires are all probably too small in diameter to support a vortex wall because a vortex takes a certain size. So these might be transverse walls where one moment switches, then the other, and so on. Now, the problem with fork, though, is that because you're taking a double derivative, remember, let me show you this one more time. We're talking about, is the slope from one line different from the line above it? That's really what we're plotting. And so these slopes are all the same. So at these reversal fields, there's not much of a fork parameter, that the double derivative, meaning the slope is the first derivative, and is it different from the line below it? These are all about the same slope. So the slope changes when you get over to this part of the curve, and that's why fork is saying we are measuring when do wires switch back. That's how we're able to separate the coercivity from the interactions. But that's also why you have to measure all of those dots, because when you apply a saturating field and hop to some reversal field, and then you sweep back to saturating, you don't really know, unless you already know your sample pretty well, where it's going to switch. So you have to measure every single one of those fields all the way back, and you can see each one of these switches back at a different applied field. But because you're doing a double derivative, it's incredibly noisy. And most fork programs that are out there, most fork papers, they will talk about the smoothing factor. So if you happen to have noise, you might have your slope look like it's really positive and really negative, but actually it's just noise. So you have to take an average to see what is the actual slope of the curve. And you can see here, if you have a smoothing factor of 4 or 10 or 20, the fork parameter can look pretty different, and the heat map can look pretty different, even though it's the exact same measurement, just processed in a different way. So we started talking with Peter Fisher, who made this. It's a free program. If you want to measure fork, it's called Fork Plus. And the way most DSMs or AGMs measure hysteresis loops, a lot of them have a program for fork as well, especially Lakeshore, that sells a lot of these vibrating sample magnetometers or alternating gradient magnetometers. They have a program that'll measure fork for you and generate these heat maps. But Peter has this shareware that he's put online where you can process your data using what he calls Fork Plus. And he just makes successive positive and negative show up as orange and blue, which are opposing colors. So they just look gray. And it's only when you really have all the dots in an area with a pretty high signal in the same direction that you really see a fork signal. So you could say really there's no smoothing in the Fork Plus. And then maybe compare the others to that if you want to say this is real, what do the actual heat maps look like? And Rez has actually gone through and done that in this paper that I have cited here. But meanwhile, we were talking with Peter. And Rez and I had been processing the fork data, not using the programs and the algorithms, but just thinking about the data on our own. And we noticed that if you have nanowires that are very narrow and very, very skinny and very far apart, so they're going to have a high coercivity and not interact with each other much. There's a very big difference between that fork and large nanowires that are really close to each other. So these 200 nanometer diameter nanowires are going to be able to form a vortex wall, or even maybe a vortex in the whole structure and switch that way. But they're also next to each other. So when their moments are up, they're going to really be exerting a down moment or field on the wire next to them. So here's what the fork curves look like. You can see they're dramatically different. And we just got thinking about, what's really happening on this side of those fork measurements. Instead of measuring all the way back and looking to see where the slope is different from the one above it, what about the fact that in this case, you switch to here and, you have apply this reversal field. There's not much slope to this before it switches back, right? So you apply a saturating field and you hop to this curve, to this field, let's say minus 100 Oersted. Well, at that point, actually that's 1,000 Oersted. I have my, this is in millitesla, so I have to remember there's a factor of 10 there. So I apply minus 1 kilo Oersted, and really about half of my wires switch the other way because my total moment is about 0. And then they switch back somewhere around like 4 or 5, well, maybe 5 to 900 Oersted, and then you saturate again. Come back to a negative, another reversal field, and more of them switch, but they don't really switch back until they really switch at a certain coercive field. As opposed to wires like this, where you can see even when you first come off that reversal field and start to sweep back, a lot of the wires are already starting to switch. And we were thinking about how exactly could we use that? Call it maybe a reversible moment that switches back right away compared to an irreversible moment that stays switched until you hit the coercive field. And as we were talking about that, and we had Peter visit, he's an alumni from actually the University of Minnesota High School, which is kind of funny. We used to have a high school. His dad was a professor. Then he went off and got a master's and PhD and worked at Alabama as a professor for a long time. We started telling him what we were trying to do was actually plot that slope as a function of the reversal field. And that we could see that when the wires were far apart and very thin, so high coercivity, that we got something like 1 Gaussian. But if the wires were very wide in diameter and close together, it almost looked like we were getting 3 Gaussians in that slope that was occurring right at the reversal field. And he said, oh, mathematically, that's the same as projecting your fork heat map onto the reversal field axes. So that's what I'm showing here. Picture taking this heat map, which is like a mountain, because the red going to purple represents a higher, coming out of the page, a higher fork parameter. And if you project that parameter onto the reversal field axes, you end up with this Gaussian. But when you have this kind of T structure, it's not that there are some nanowires that have very high coercivity and some that have low coercivity. These are actually the highest coercivity nanowires that switch when the interaction field is the highest. And so it's kind of hard to see that when you're just looking at a fork curve, but the projection on the HR axis shows it exactly. So we were pretty excited about this idea that you could project the fork diagram and then tell a lot about your sample. And one of the reasons we're really excited about it is you can measure in 50 to 100 fewer points. And there's no smoothing when you take the projection on the HR axis. So to put this in perspective, Reza often works when everyone else is on vacation or break. I believe the data I just showed you for these 30 and 200 nanometer wires were taken over Christmas break, I think in 2019, because that's when no one was using the machine. And some of those fork curves take 30 to 40 hours to measure. So literally days for one sample. Then you put another sample in, you have another couple days of constant measuring. So if you could reduce from 40 hours to 4 or to something like 0.4, which would be like 40 minutes, let's say, it would be amazing to be able to take a similar amount of data in 40 minutes that used to take you 40 hours, right? So let me just make sure that that whole concept is explained well. Here's the standard fork. You have to jump to here and measure each one of these loops one after another. But when you do this projection, you can take the slope right at HR, which means you only need a couple points, maybe even 2 if you wait for a while. And it's actually easier to wait for a while than to apply a new field and then wait for a while if you want to think about time. But then we have this, which is called the irreversible switching. So reversible is the slope, but what's left after that slope is subtracted is the irreversible, the wires that are still pointing left, even though we have started to remove the reversal field. That's what I'm talking about. So you can see the number of points being measured right here, which is our projection method. Those are the only points we need for the projection method compared to all those points you need for the fork measurement. And we're really talking about like 100 curves and 100 points per curve. It's a lot of measurements. And this is the math that explains why just taking the difference in those slopes, just subtracting this slope away is actually this parameter right here. And this is just a change in moment when you get out to h equals infinity. So there's no change, there's no slope in your data once you've saturated. So for h equals infinity, that implies after saturation. So this term goes to 0. So literally this term, which is what we're plotting in our projection curve, it mathematically is a projection of that fork diagram onto the HR axis. Now, Reza then realized, you know, if we're gonna do that, why not go all the way back to what's reversible and what's not reversible? Meaning, why don't we go back to what's called backfield remnants? So you saturate, then you go to a reversal field, and then you just remove the field and measure the moment at 0 field. Saturate again, go to another reversal field, and then take the field away. And actually, those are pretty fast measurements to take, and they've proven to be very key to identifying wires when they're next to each other and even in a mixture, which is very exciting. There's been a lot of people who talk about barcoding using nanowires, but how actually do you read out that barcode is not trivial. So I've gone a while, and I'm going to switch into applications now. I want to make sure if there's a question. Now, Mehdi, I was thinking colloquium's often an hour. Is that true?
Yes. Yeah, we
Okay.
still have 20 minutes. So
Good. Okay, because I'm about to go in the applications. I'll try to end a couple minutes early for questions because I know it's
sounds good.
let's have somebody running over 5 or 10 minutes, so I'll be careful.
No worries.
All right, so great. So the applications that I want to talk about today and how we apply some of these things we figured out are biocomposites, which could be sort of internal band-aids, actually. The polymers that we're using are used for things like bone, to hold bone in place while it's recovering, and other internal applications. So that's one of the reasons we like those polymers. And we're going to load them with moments. Then we'll separate the wires so they're free floating and how do they interact with cells. And then I want to get to this new application where we're going to nano-warm cryopreserved organs. So application 1 are these biocomposite labels. What I'm plotting here is that projection I just told you about of the irreversible switching on the reversal field axes. And Reza just plotted here 30, 50, 100, and 200 nanometers. So 4 separate samples. And you can see that their projection on the HR axes is, you know, pretty distinct. There's some overlap. And when you get to the 200 nanometer ones, like I showed you, there's kind of 3 Gaussians there. So it's a pretty broad peak. But maybe we'll say, well, we're not going to use 200 nanometer diameter wires for barcodes because their peak is too wide. The other 3 are actually still quite interesting. And this is cobalt, same parameters, but using a higher moment material. And you can see how that projection peak widens out a bit. And then what he's done is actually combine different mixtures, so 30 nanometer nickel with the 30 nanometer cobalt, and measured the dots that you see as a measurement of the combination. And because he knows what the single wires look like, we sort of use those like calibration curves. And he's also normalized it to 1. This is another factor that he's looking at with the projection. It's actually the this milli EMU over Orsted is that fork parameter that's been projected on the HR axes. And so mostly what I want to say is just you can see that you could very clearly tell the difference that you have for sure here a 30 nanometer cobalt mixed with a 30 nanometer nickel. And you could even tell how much of each you have by volume because they have a very specific EMU per gram or EMU per cc moment that they carry with them. Now, this is a little trickier. He's mixing 30 with 200. You actually could pull this out because this little blip that happens in the peak of the projection is abnormal. So you probably would say, well, there's something else in that mixture. It's not just 200 nanometers, but clearly it's not as well defined as the others. And then he just steps through different cases. You can see when it's very easy to distinguish compared to some cases where you can't distinguish the two barcodes at all. So these are just different examples of mixing barcodes. And then he also realized, like, this was really a nice thought. He said, well, I know I have a symmetric distribution, whatever it is. So if it turns out that what I do instead is take a derivative of both curves, right, or a derivative of the total, the cobalt and the nickel are, the derivative is very far apart. And if the derivative, meaning the slope of that peak I just showed you on the left side, is starting to run into, depending on certain mixtures, right? Like if this mixture here, the slopes are very close together. Sometimes, like in this case, it turns out that the slope on the other side is far apart because the center of the peaks is different and they're symmetric. You can end up using the derivative on the other side of the peak to still give you a pretty clear indication of what two barcodes you have present. So there's multiple things we can do now instead of just having one value. Nickel has this coercivity, cobalt 30 nanometers has this coercivity. Can we see those two coercivities by taking a hysteresis loop of a combination? I promise you, you can't see that. But when you do these measurements here, where you take a fork curve, do the projection method, so you only have the same number of points as a hysteresis loop anyway, and plot that in this way, you can very clearly tell the difference between your barcodes for all but about 14 of these, 4 of these 16 combinations aren't very distinguishable, but 14 combinations just from cobalt and nickel, you could easily tell apart. And then he has measured inside organs to kind of make sure there's not like an oxidation or some other problem that he would have. And so we're starting to think about what we could actually apply these to with bio. By then, of course, we would start to collaborate with somebody in the bio fields. So here is the next thing that he did, which is decoding. He just started thinking, well, I'm always like comparing and doing this on my own, but could I really just feed that into like a detector that would tell the user what codes they have if they had no idea what the codes might be? So what we'll do is give them like 8 different options, right? Cobalt and nickel, and we'll have 30, 50, 80, 100, and 200 nanometer diameters. And then we'll measure the sample and ask the detector to tell us how many and what barcodes are present. So he worked out this algorithm where it matches, like here's the experimental curve, and actually the measurement is the blue points. And then he said, okay, what if there was just one present? Let's see if I'm doing this right. Yeah, and then, oh, and you know, it's not a very good match, right? It doesn't match at all. So clearly there's not just one barcode present. And I mean, our eyes could have seen this, but we're assuming no one's looking at the data. We're just feeding it in a machine and a doctor would get the output, not someone who knows magnetics. But the algorithm would say, yeah, there's not a match. There's more than one barcode. What if there's 2? Well, if there were 2, it would be this one and this one. And then it says, what if there were 3? And when it gets to 3, you see this RMS error between the guess of 2 and the guess of 3 didn't get much better. So in that case, it would say, no, it can't be. It must be 2. And actually, he was able to identify, without knowing ahead of time how many and which barcodes were present, he could tell that from these algorithms, except in a very few cases like those 4 out of 16 that I already mentioned, they look like this. There's too much overlap between the different barcodes. So the algorithm would say, oh, there's only 1 present, even though there were 2 present. But in that case, we would already know ahead of time when we're labeling samples, you can't use that combination because you're not going to be able to tell those apart. So that means we now have, just from 2 types of materials and 4 types of diameters, we already have 12 different barcode that we could distinguish automatically using this algorithm. Meanwhile, in talking with my colleague, Rhonda Franklin, who does high frequency materials, which I think is really great because her name is Rhonda Franklin, so her initials are RF, and she does radio frequency. We started thinking about one other thing with moments as they resonate at different frequencies. And you can pick out that resonant frequency that is a combination of the frequency in the field, being a DC field being applied. So there's a pretty well-known Kittel formula, which is in red here, And what it basically says is, even if the wires are effectively applying a field on each other, you really only have the parameters of saturation moment and that fill factor or porosity, and you can control that effective field. So we've put samples onto coplanar waveguides, a couple different kinds that her student Wen Zhao. I hope you've noticed I try to pick out the student that did the work and the paper reference. And when there's a collaborator, I put them in parentheses, just so that's what the footnotes are all the time. Anyway, Wen was able to measure using this idea. This is just what I plotted of every single one of these lines is measuring the absorption of that signal coming out of the coplanar waveguide at different frequencies as you're applying a DC field. So for example, you apply 20 gigahertz as your RF signal, and then you sweep the field from 1 Tesla to 0. And then you apply 38 gigahertz, and you sweep the field from 1 Tesla to 0. And as you do that, and you apply different frequencies, or if you're clever and you're sweeping frequencies at the same time, but at a rate that you can get all of these curves at once, which there are people who have done that when they were simply looking for the FMR peaks. But what we were interested in is, can we mix samples and still be able to distinguish what we have? And it looks like this may be an option, but so far, this isn't really a hands-off method. The methods that Reza and I have been developing are really where you could take an organ and put it in VSM or something. And if you don't have to apply a very high field, you could sweep the field and tell exactly what's in there. All right, so application number 2 is cells. I'm just going to kind of step through a couple fun pictures. We noticed that the nanowires move with an external magnetic field, right? These are just sitting in an assay. We're like, hey, we can control them. Meanwhile, I had met Jaime Moriano on a university committee, and he works with dog bone cancer and gave me this cute picture to put in my slides right when you're getting a little tired. So we're going to take dog bone cancer cells and mix nanowires with them. And what you'll see here is basically the cells like to move, and we've labeled them so that they like to attach to the nanowires. We label the nanowires. So they like to attach to the nanowires because they actually think the nanowires are the extracellular matrix. So they're kind of looking to form a metastasis site, unfortunately, but instead they pick up a nanowire. And as there's certain clumps here, but what you'll see is these clumps get dispersed by the cells. So the cells themselves break up any clumping that happened. This is just because they happen to settle. It's not that they're magnetically stuck to each other. So over time, the cells have dispersed those nanowires by grabbing them and walking away and internalize them after that. So here's various images where there's vesicles. The cells like to internalize with this endocytosis process. Then there's a vesicle that has a nanowire inside of it. And we have several papers now that are just showing where are the wires and what are they doing. And even at this point, we know that they get exocytosed or spit out of the cell, holding on to exosomes, which is very exciting because cancer studies are really aiming at exosomes over circulating tumor cells as one of the first indicators of where metastasis might happen. So we're pretty excited to start this study. And we've just shown that the nanowires aren't very toxic unless we want them to be. So once the cells pick them up, they live normally, they have a good metabolic activity, but we can then turn on the magnetic field to kill them if we want to, like if they're in a cancer cell, or to heat them. We've also isolated some white blood cells, so I'm just kind of showing this, ones that are specifically able to be used for immunotherapy against cancer. Our colleague Mark Jenkins, we were talking with Jaime and had this idea and gave it a try, and it works pretty well, so you can look at that paper if you're interested in immunology. But I really want to make sure I have time for nanowarming, which is the last application. We have a new engineering research center just funded last August by NSF to try to study the idea that you could bank organs and people that need organ transplants would have one available. So right now, if someone were to pass away and had on their license they want to donate organs, or even if you want to be able to save a kidney for yourself later because you know that you have a disease that's going to progress, even if you want to save a tissue, undergo the surgery where you take a vessel out of your leg, but you want to freeze it and be ready so you're stable again when you want to go ahead and put that in a bypass. There's various reasons why you might want to preserve tissue or organs. So this is about the distance that an organ can survive today or time, I should say. And because of that time, it limits how far, if you have an organ donated, where it can go. And the recipient has to be healthy enough to undergo pretty dramatic surgery within 4 hours. Like right now, drop everything and go to the hospital and get ready for surgery. But if instead you could cryopreserve even a week, you could basically go anywhere with an organ, which would be, my own license says I'm happy to be a donor, but I know that I could probably only contribute to people in Minnesota because of the timing. So what drove this is that we know that when you freeze cells, you can recover them. But when you freeze tissue and you try to heat it up the same way, you crack it's too big a sample and you end up having cracking or crystallization. So if you could spread magnetic nanowires throughout that sample, you'd have uniform heating throughout the sample, and you could heat it externally with this magnetic field, and then you go ahead and recover that tissue and put it back into the place you need it. The key is, though, these cryopreservation agents, there are other people figuring out how to cool large masses well, but they still can't heat the mass as well. And that's because you have to heat pretty fast. So here in Minnesota, when it's winter, sometimes you have a lake that freezes and you can see through the ice. And believe it or not, we were walking on our lake here in December because we hadn't had snow yet. And we could see through the ice as we walked on this big lake that's near me. But when it heats up, it turns white because it heats too slowly and the ice crystallizes as it's heating. So you made it cool down and stay viscous, but on heating, it crystallizes. So what we're going to do now is all of the studies so far are with these oxide particles where they put different coatings on them to try to get them to heat faster and faster. So they can do like 55 to 100 degrees a minute. For the one cryopreservation agent, which is like a biocompatible antifreeze, they have to go faster than 50 degrees per minute. And they're starting to get there with these iron oxide particles. I'm going to kind of hop through. The key is, though, the hysteresis loop is where you get the heating. And the green is the iron oxide particle, and the red is our iron nanowires. So you can just see that we could provide a lot more heat per particle than you can get from iron oxide. Lower moment and a lower coercivity. You also have, in any electromagnet, a distribution in fields. So if you really want uniform heating in a non-uniform field, you have to optimize your coercivity. All of the nanowires have to heat. They have to all go around the hysteresis loop every time you switch the field from plus to minus. And you've seen now we are pretty good at controlling our coercivity. So I'm going to kind of skip this, but basically say this is what the nanoparticles are able to do right now. This is the critical warming rate. So you freeze something to liquid nitrogen temperature and you want to heat it fast enough to avoid crystallization. You have to get on this side of that critical warming rate. So they have some particles that can do it now. And you see that this is like 100, takes about 100 seconds to heat up to melting. And this is our nanowires. I just want to remind you, when I say nanowire, they're this big compared to a red blood cell. So they're really small, even though they have aspect ratio of 1 to 20 sometimes. And I just want to remind you that the other curve, this critical warming rate, is still the dotted line. And with the nanowires, they're really only nanoparticles. They can get to zero or melting at about 100 seconds, and we're getting there in like 18 seconds. So that means we're going to be able to increase the concentration of the antifreeze, or even use some of the safer biocompatible antifreezes because we can heat so fast. So we're just starting this with John Bischoff. We worked on this one paper with him before he got the center, but now he has the Engineering Research Center, and our group is part of that to try to make these nanowires more and more stable in the cryopreservation agent and heating faster and faster. Yep, so right now we're just heating cryopreservation agent in a vial. He has actually heated vessels like arteries that are viable after being frozen and rewarmed with the iron oxide. So we're going to try that next. And maybe at some point we can actually freeze a heart and warm it up. So I just want to end with this conclusion, which just reminds you, I showed you we can design and synthesize these nanowires of all different kinds. They're a lot smaller than like if you do biomagnetics, you might use Miltenyi beads. We measure them a bit with coplanar waveguides and a whole lot by thinking about how to measure the moment as we apply different fields. And then our applications are the biocomposites, labeling cells, and just recently this nanowarming. So that's all I have for you. I guess I just made the time instead of having too much time for questions, but I was looking for the chat. I don't think anyone's asked a question.
So thank you so much for such an exciting and inspirational talk. It was a lot of cool ideas and
Cool and hot.
yeah, especially I think you brought a lot of applications that I hadn't even thought about, like cryopreservations and the problems that one has to deal with there. So I actually had a few questions. So in I think it was slide 25, yeah, I guess the cancer work that you were doing. So just one question I had was, were the nanowires, were they labeled with any like biorecognition element, like an antibody or anything there, or no? Was there, what exactly was the
In this
bonding
case,
method of binding?
we had PEG, and then we put RGD on the PEG. So actually, that's why PEG, it makes it call it the stealth molecule. The cells don't really see the PEG. They don't really like the PEG. They just sort of let the PEG exist among them. And so when we add nanowires that are bare, we've lost some cells compared to not losing cells, but compared to silica particles, which are pretty popular, we don't lose too many. But if we coat with PEG, we lose less. And if we coat with RGD, which is, it's a peptide that's actually on your extracellular matrix. So these cells think they're sitting in extracellular matrix when they see a nanowire coated with RGD. And that's why, when we put in bare nanowires, the more you put in, the more toxic. The lower the metabolic activity. Sometimes I have a talk where I have these cells going to a gym and they say, I feel great. The metabolic activity is going down for bare wires. Kind of stays the same for PEG because the cells don't like the PEG, but they don't mind having more or less of it. But when we coat with RGD, actually, they really like the RGD coated nanowires because they think they're sitting, in the extracellular matrix.
I see. Okay. So I guess one question related to that is in general, how easy is it to functionalize the wires, like with different kinds of peptides and antibodies or
Yeah, it's
aptamers?
actually, pretty much all of the techniques that are out there, we use those for nanowires too. So the RGD we put on because we have, the standard kind of carboxyl with an amine, and then the histamine is another one for coating nickel. And if we have that on a PEG, then on the other side of the PEG, we put whatever we want. And sometimes we use dodecanoic acid, which is a very short PEG, basically. Yeah, but RGD is especially good because osteosarcoma overexpresses the integrin that attaches to your extracellular matrix. That's why it's kind of bad at metastasizing. But it means that if we put just RGD-coated nanowires in a mix, the osteosarcoma is going to pick up like 10 times more nanowires than a healthy cell.
I see. Okay. So one other question is related to the readout instrumentation, which you're using to detect the magnetic fields and the magnetic moments of the particles. How easy is it to make that small and portable if you wanted to to take this point of care ultimately?
Yeah, there are several fairly small VSMs and AGMs. So if you want to use that technique, but it is one reason why we were looking at the coplanar waveguides, because really all you need is a known magnetic field. And, permanent magnets go up to like 5,000 Oersted. So you could even at some point have a couple permanent magnets and move them to different distances to apply a field, which could be very small. But then you would need to measure the moment. And that's something that the coplanar waveguide or even like an antenna setup could do. If you know what frequency you're after because you know your barcode.
Oh, okay. No, that makes sense. So maybe you have or haven't thought about this. Do you know if if impedance can be used to detect these wires, particularly like at higher frequencies? Would you know if anything interesting would show up?
I do think it will. You know what? You could actually model these things as having a changing mu. So I think in a lot of the high frequency measurements, you have a pretty easy change in epsilon, but it's pretty hard to change mu. And so these wires could let you do that.
I see. I know that sounds very interesting. And so have you also looked into like using the nanowires for separating cells for complex mixtures like circulating tumor cells or even viruses like SARS-CoV-2?
Yeah, well, right now we just have this one, it's actually down here. We did do this one where we had basically blood and we separated out the 24. It could even be there was a combination of white blood cells here.
I
And we
see.
separated out the ones that had CD4 plus, which is what they were interested in to be able to train these to kill cancer. The unfortunate thing on this particular study was that our nanowires can settle. So that's why we're looking at like how much egg do we put on them so they're buoyant. So they don't stick together and clump and fall out. They don't precipitate out, but they can settle. And that's where the peg can give them buoyant force, which means they stay in suspension longer. Yeah, but the idea here is, this polymer, it can only attach to 4 different CD4 antibodies. And so it doesn't really grab the cell very well. The other thing that happened here is our wires are so magnetic, they just ripped across the solution when we applied a magnetic field. So we could see that they attached to the cells, but when they were collected, they left the cells behind. So we need to find a way to bond stronger to the cell, which just has to do with the, the biochemistry. And there's many applications out there. We just have to buy that one next.
I see.
That antibody bond.
So there's a question in the chat that came up. It says, it's from Mohammed Tayyab. You mentioned coplanar waveguides to measure the magnetic field. Can you maybe go into more detail how that works? What is the parameter of interest when using coplanar waveguides?
So in that case, what we're actually doing is we put the sample on a coplanar waveguide, like this. This is our sample right here, this black thing. And so we put that into a magnet, the 2 poles of an electromagnet that just applies a DC field. And then we just run the AC signal through the coplanar waveguide. And that means that we have an AC field that's wrapping around the coplanar waveguide like this. And this right here is our nanowires. So when you have a DC field that's perpendicular to the AC field, then you have a certain resonance where the moments kind of resonate with the AC field. So we kind of jokingly call it like a swing, where if you want to push somebody, you want to have a certain frequency you're pushing them at because there's a certain resonance to the swing. And if you try to push at a different frequency, there's not a very good swinging going on. So same thing here, there's a resonant frequency that the moments want to spin at like a yo-yo. And so when that condition is met, all of a sudden you get a lot of absorption of the AC signal. And that shows up, and this is when the electric field is the DC field is parallel to the nanowires, but the AC field is still perpendicular. Then what you measure is a absorption peak, basically, or a null in the AC signal. So if I were going to apply, let's say, 34 gigahertz, then I would know when I sweep from 1 Tesla, and I don't even have to go to Tesla, I could go to whatever, 6,000 Orsted to 4,000 Orsted and see if there's a peak there. And I could certainly aim for lower frequencies if I want to make sure that I don't have to apply a large DC field. Then I'm just going to look to see is there a peak there or not. And where that peak happens is what we're looking at here. So in this case, the wires are all the same, and we just changed cobalt, nickel, and iron, and we can determine that we do have those 3 wires present in this sample.
Thank you so much. So I think we're just at time right now. It was a fascinating talk, a lot of great fundamental work with very high impact applications that can impact patient care. So we do wish you the best of luck with that, and for the sake of those patients, we hope your research will be successful and fruitful. And we just wanted to thank you for the time you took today to come share your exciting research with us. Very exciting and inspirational work. And so I wish, hopefully one day we can host you in person in the not too distant future.
Yeah, thanks so much for
Yeah.
inviting me.
Thank you. So
This is also a note to students. Maddie and I met at a conference, so you have to go to those conferences when it comes
yes,
back again and talk to people that you don't know, and you'll be friends for life.
yeah, that's right. That's right. Yeah, the people you shake hands with at those conferences is really important, more than you think. So thank you again,
Thanks.
Professor Stadler, for joining us today. So if you were here, we would all clap for you, and we would thank
Thanks
you
a lot.
in person, but we'll do that virtually today. So thank you
Okay.
so much, and stay safe, and hopefully we will host you in the future one day in person.
Thank you.
Thank you. Have
All right.
a great day.
Yeah, talk to you later.
Okay, thanks. Bye-bye.